Hello. So in this video, I will be demonstrating my modular submission for CS432 assignment 2, which is a lightweight DBMS built using a B+3 indexing engine implemented from scratch in Python. So the project is structured inside a folder called as database assignment 2, which contains a database package with 5 different Python files, a Jupyter notebook report, and requirements file. So let me walk you through the file structure. B+3.py contains the core B+3 logic. Brute is our baseline. Table.py wraps into a table abstraction, wraps the tree into the table abstraction. dbmanager.py manages multiple tables, and the report by ipynb file is where everything comes together, and we can see the report. So on the screen, you can see the B+3.py file open in the editor. The B+3 node class has 4 fields: keys, values for leaf nodes, children for internal nodes, and the next pointer for the leaf list. The B+3 class is initialized with the order parameter. I have used order 4 for demos and order 50 for benchmarking. The insert method handles the root splitting. If the root is full, a new root is created, and the old root is split using a split child. For leaf splits, the middle key is copied up to the parent, and the linked list pointer is maintained. New node.next equals child.next, and the child.next equals new node. For internal node split, the middle key is promoted and removed from the child. This is the key difference between the B tree and B+3. The delete method, we can see, is an full implementation with an underflow handling. Field child checks if we can borrow from the left sibling or the right sibling, or we must merge. Search traverses from root to leaf following the key comparisons, and the range query uses the leaf linked list to efficiently scan a range without traversing the whole tree again. So now we'll see the live demo. Let me run the basic operations demo. So I have inserted 7 records into the B+3 of order 4, and you can see the output after running the cell. Search for the key 15 returns Dave, and search for the key 19 returns none. So the key doesn't exist, obviously. Range query from 5 to 20 returns all the key value pairs in that range. As you can see, 5 Carol, 10 Alice, 15 Dave, 20 Rob, retrieved efficiently using the leaf linked list. And you can see also get all returns all the records in the sorted order. This confirms the tree is maintained in the sorted structure correctly. After update, you can see the key 15 now holds the updated value, and after delete, the 15 key returns the none, and get all confirms that it's removed from the tree, while all the other keys remain intact. So before deleting and after deleting, so you can see cell 4, which I have numbered, we can see the graphics tree visualization. I have inserted 12 keys into the B+3 of order 4. By running the cell, we can see the output. The blue nodes are the internal nodes. They act as the routing guides, storing only keys for navigation. The yellow nodes are leaf nodes. They store both the key and the associated value. As you can see, the tree is perfectly balanced. All leaf nodes are at the same depth. The leaf nodes are ordered from left to right, and invisible ordering edges in the same rank subgraph maintain that linked list structure. Internal node keys are separator keys. Notice each separator is a copy of the first key on its right child. This is the B+3 property. Now you can see the table class wraps the B+3 structure into the high level SQL like abstraction. So as after running the cell, you can see I have inserted 5 student records as Python dictionaries with names, GPAs, and department. So as you can see, the select 103 returns the Carol's full record. The B+3 is storing the entire dictionary as a value. The range query from 101 to 103 returns Alice, Bob, and Carol in the sorted key order. The aggregate method computes the average GPA as 3.62 and maximum GPA as 3.9. The after update and delete, as you can see, select all confirms only 4 records remain, which all are in the sorted order. The database manager allows creating, accessing, dropping multiple tables by the name, acting as a simple in-memory DBMS. Now the most important part of the video, that is performance analysis. The performance benchmarking comparing the B+3 against the brute force DB across the dataset sizing from the range 1000 to 10,000 records. Look at the summary table. At 10,000 records, you can see the B+3 search is roughly 8 to 10 times faster than the brute force. And we can also see the graph. In insertion time, as you can see, the brute force is faster here, which is expected. Python list is appends in order 1, while the B+3 insertion is order log n. With tree travels and occasional splits, both grow slowly, confirming the time complexity. We can also see the search time. B+3 is significantly faster. The brute force grows linearly, order n. Because it scans the entire list, B+3 is order log n. The gap widens clearly as n increases. We'll also see the range query time over here. B+3 wins convincingly once we reach the start leaf via order log n traversal. We scan only the relevant range using the linked list. Brute force must scan every element in order n, even for a small range. Deletion time, you can see the brute force deletion is extremely slow. List.remove is order n because it must find the element and shift all the subsequent elements. B+3 delete is order log n. The gap here is the largest. In the memory, you can see the peak memory usage table. The tree uses significantly more memory due to the tree node objects, pointers, internal nodes overhead. Brute force stores only a plain Python list of integers, which is much lighter. And this is the classic time space trade-off. Overall, the benchmark confirms that B+3 is purpose built for road heavy and query heavy workloads, which is exactly why the real databases like MySQL and PostgreSQL use it as their primary structure. So to summarize, our group has implemented a complete B+3 from scratch with insertion, deletion, with merging, redistribution, exact search, range queries, value storage, and graphics visualization. I have built a table and database manager abstraction on top of it and concluded through the performance comparison against the brute force baseline. The results clearly demonstrate where the B+3's excel, search, range queries, and deletion, and where the trade-off lies like high memory usage and the slower raw insertions compared to a simple list. Thank you.